575,000 kilograms. That is the maximum takeoff weight of the Airbus A380, the heaviest passenger aircraft ever certified for commercial flight. To put that number somewhere concrete, it is roughly equivalent to a fully loaded freight train. And yet, 4 times a day at some of the world's busiest airports, one of these machines accelerates down a strip of asphalt, pulls its nose skyward, and climbs to somewhere between 35,000 and 40,000 feet, where it cruises at 560 miles per hour for 12, sometimes 15 hours, above the weather, above almost everything. That is not a minor engineering achievement. That is the result of over a century of physics working exactly as intended. If the mechanics of flight are the kind of thing that keeps you watching, subscribe to Aviast and drop a like, every one of them genuinely helps us keep going. The story does not begin with jets. It begins much earlier, and much more modestly. In the early 19th century, a British engineer named Sir George Cayley did something that seems obvious in retrospect but was genuinely radical at the time. He separated the concepts of lift and thrust. Before Cayley, most people who thought about flying imagined something like a bird, a single system doing everything at once. Cayley realized that a wing needed a specific curved shape to generate upward force, and that forward motion had to come from somewhere else entirely. Decades later, a German engineer named Otto Lilienthal took that idea into the air. He made hundreds of glider flights, methodically studying how air behaved around a curved wing surface. He was killed in a glider crash in 1896, but the data he left behind was invaluable. Then came December 17, 1903. 2 brothers from Ohio, Orville and Wilbur Wright, took a powered aircraft to a beach in North Carolina called Kitty Hawk and proved that a heavier-than-air machine could achieve controlled, sustained, powered flight. The first flight lasted 12 seconds. It covered 120 feet. By the end of that same day, their 4th attempt covered 852 feet in 59 seconds. Those numbers sound modest. The implication was not. Progress after that was rapid, and largely driven by necessity. The First World War accelerated engine technology, airframe design, and aerodynamic research in ways that peacetime investment never would have. Wooden structures gave way to metal. Aircraft became faster, heavier, and far more capable. By 1952, the de Havilland Comet entered service as the world's first commercial jet airliner. In 1970, the Boeing 747 connected continents at a scale that had never been possible before. And eventually, the A380 demonstrated that a 500-ton aircraft could be not just airworthy, but genuinely efficient, quiet, and stable at cruise altitude. The core principle underlying all of it, however, never changed. Every aircraft in flight, from the Wright Flyer to the A380, is governed by 4 forces. Weight pulls the aircraft downward. Lift, generated by the wings, acts upward against it. Thrust, produced by the engines, pushes the aircraft forward. Drag, the resistance of the air, works against that forward motion. The relationship between these 4 forces determines everything that happens in flight. When lift exactly equals weight, the aircraft holds its altitude. When thrust exactly equals drag, it holds its speed. Any imbalance produces acceleration in the direction of the net force. No magic, no mystery, just Newton's laws operating at scale. The part most people misunderstand is where lift actually comes from. The explanation that circulates most widely goes like this: air traveling over the top of the wing has a longer path to cover than air beneath it, so it must move faster, and faster moving air produces lower pressure. That explanation is incomplete, and in some versions outright misleading. Here is what actually happens. A wing has a specific cross-sectional profile, curved and thicker on top, flatter underneath. This shape is called an airfoil. During flight, the wing is also angled slightly upward relative to the oncoming air. That angle is called the angle of attack. As air flows around the wing, the flow over the upper surface accelerates. Pressure above the wing drops. Pressure below remains comparatively higher. That difference in pressure produces an upward force. But pressure difference alone does not tell the whole story. The wing is also deflecting air downward, a phenomenon called downwash. Newton's third law states that for every action, there is an equal and opposite reaction. The wing pushes air downward, the air pushes the wing upward with equal force. Bernoulli's principle and Newton's third law are not competing explanations. They describe the same physical process from two different perspectives, pressure distribution on one side, momentum transfer on the other. Together, they account for the lift that holds hundreds of tons in the air. The angle of attack is one of the most important variables a pilot controls. When a pilot pulls back on the controls during takeoff, the nose rises, the angle of attack increases, and the pressure distribution around the wing changes, more aggressively accelerating the air over the top surface, increasing downwash, and raising what engineers call the lift coefficient, abbreviated CL. Higher lift coefficient means more lift. But there is a hard limit to this. Push the angle of attack too far and the airflow over the upper surface can no longer follow the wing's contour. It detaches. The pressure distribution collapses. Lift drops sharply and suddenly. That is a stall. This is why speed matters so much. In the lift equation, velocity appears as a squared value. If an aircraft doubles its airspeed, lift increases by a factor of 4. Cut the speed in half, and lift falls to 1/4 of its previous value. The airplane has to be moving fast enough, relative to the surrounding air, for the wings to do their job. That is why aircraft cannot simply jump off the runway. They must accelerate to the point where aerodynamic lift equals the aircraft's weight. At that moment, and not before, the normal force from the ground drops to 0. The aircraft does not jump into the air. It simply no longer needs the ground. When an aircraft needs to fly slowly, during takeoff or landing, the basic wing shape is not enough. Look out the window just before takeoff and you will see it happen. Panels extend from the rear of the wing, those are flaps. Panels extend from the leading edge, those are slats. Together, they do three things. They slightly increase the effective surface area of the wing. They significantly increase the curvature of the airfoil, a property called camber. And they dramatically increase the lift coefficient. The slats serve a second, equally important function. The gap they create allows higher energy air from beneath the wing to flow over the upper surface, helping the airflow stay attached at steeper angles of attack. This delays the stall. It is why a 400-ton aircraft can safely operate at the relatively low speeds required for a controlled approach to a runway. Cruise altitude, typically between 35,000 and 40,000 feet, is not chosen arbitrarily. At that height, the atmosphere is far thinner than at sea level. Drag depends directly on air density, and thinner air means dramatically less resistance. Less drag means less fuel burned per mile. The cold temperatures at altitude also improve the efficiency of jet engines. There are fewer weather systems to navigate, less turbulence from terrain, less surface heating driving convective activity. And as fuel burns off during a long flight, the aircraft becomes lighter, allowing it to gradually climb even higher, a procedure known as a step climb, squeezing further efficiency out of every remaining kilogram of fuel. Takeoff is a precisely sequenced event, not a simple application of full thrust. Before the aircraft reaches the runway, the crew has already calculated three critical speeds. The first is V1, the decision speed. Past this point, there is not enough runway left to stop safely. So the takeoff continues regardless of what happens next, including an engine failure. The second is VR, rotation speed. At this point, the pilot applies back pressure on the controls, the nose lifts, the angle of attack increases, and lift builds rapidly. The third is V2, the minimum safe climb speed with one engine inoperative. This speed guarantees the aircraft has sufficient performance and control authority to continue climbing safely even under degraded conditions. These numbers are specific to the aircraft's weight, the runway length, the temperature, and the altitude of the airport. Nothing about it is approximate. During the ground roll, the landing gear carries part of the aircraft's weight. As speed builds, the wings take over more and more of that load. At liftoff, the gear's contribution drops to zero, not because something changed in the aircraft, but because physics reached a threshold. From that point, the aircraft is entirely supported by aerodynamic forces. Descent and landing operate on the same principles, applied in reverse. Pilots reduce thrust and allow lift to fall very slightly below weight. The aircraft descends in a controlled, shallow glide. Flaps and slats extend again, raising the lift coefficient and lowering the minimum safe airspeed. Just before touchdown, the pilot raises the nose slightly in a maneuver called the flare, reducing vertical speed and softening contact with the runway. The moment the wheels touch down, spoilers, flat panels on the upper wing surface, deploy and destroy the remaining lift. Thrust reversers redirect engine exhaust forward. Brakes engage. The aircraft's full weight transfers back onto the landing gear, and the aerodynamic forces that kept it airborne for hours quietly stand down. The next time you watch a fully loaded widebody pull off the ground, it is worth knowing exactly what is happening in that moment. 575,000 kilograms finding equilibrium between four forces, each one calculated to the decimal point, across a machine built to do this tens of thousands of times over its operational life. What part of this process do you find hardest to intuitively grasp? The way a wing generates lift, the stall mechanics, or perhaps the precision of those takeoff speeds? Leave your answer in the comments. There is genuinely no consensus on which aspect surprises people most, and the range of answers is always interesting. If this is the kind of content that makes a flight more than just a seat and a window, subscribe to Aviast. There is a lot more where this came from.